Hi there. Thanks for joining us yet again. This is Space Nuts. My name is Andrew Dunkley, your host, and it is so good to have your company, and I hope you're well. Coming up on this particular episode, Artemis 2. Yes, the mission to the moon. We have an update for you, and it's really good news. Could we have discovered a wormhole? That's a big question. And an Einstein cross has been spotted. They marked it with a cross and then drew a circle around it. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's here again to unravel all the ravelment of space science. His name is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. I think actually we're probably as good at ravelling it as we are unravelling it, really.
I tend to agree, yes. You're absolutely right.
Yeah,
before we get into today's topics, you are in Melbourne, I believe, attending a conference.
I am, yes. Sunny Melbourne, which it isn't at the moment, although it was briefly this morning. 4 seasons in one day is what they say about Melbourne.
It's got a reputation for that.
And I think we've had it already this week. So the conference I'm at is at Deakin University here in Melbourne. It is called AstroEdu, or AstroEdu, for Astronomy Education 2025. And it's actually an international conference. I think I'm right in saying it's sponsored by the International Astronomical Union. So it's a conference of international astronomy educators. And so quite a lot of it is about the theory of education as applied to astronomy education. Quite a lot of it is about the practice of astronomy education. So there are real teachers here who teach kids, from kindergarten to year 12 and university as well. And one or two astronomers as well. And we're there because we're interested in education. I am only an amateur educator, but a professional astronomer. So my talk yesterday was about the possibilities for using mega constellations in astronomy education, because there's quite a number of ideas that come out of, what you and I talk about routinely, the mega constellations. A lot of astronomy in that, and in terms of trying to perhaps provide some background in astronomy education that might otherwise be missed. And I'm thinking of things like, how you measure the brightness of the satellites. We use the star magnitudes, the same as we do in astronomy. Why satellites are bright themselves, why radio telescopes are at great risk from satellite constellations, all of the above. But my talk aside, which was a minor contribution to this conference, there have been some fantastic presentations, really encouraging about the state of astronomy education in lands as far apart as Chile and Germany and Belgium, Sweden, Portugal, North America, Canada. Inspiring presentation from Canada this morning. A lovely chat from an educator in Hawaii, who I'll talk to later because I used to work in Hawaii a lot. So a lot of the folklore tales in astronomy he was aware of, and some of his colleagues were as well. But what was really nice was getting a shout out from a couple of this morning's presenters. They did a keynote presentation. Mari Timms and Sandra Woodward mentioned, stuff that I do and that we do, including a very nice shout out about Space Nuts, which apparently is very much a source of inspiration to talk about with kids in class.
Oh, so wonderful.
Maybe we are useful after all, Andrew.
Possibly. Maybe we do contribute a little bit to education, or maybe it's pseudoscience.
No, it's not pseudoscience.
No, it's not at all.
It's just, it's our take on the universe, which might not necessarily be the same as some other people's, but I think we're reasonably near the mark.
That's so rare in science, Fred.
Yes. So that's why I'm here in Melbourne in a hotel room. Geordie is about 1,000 kilometres away, so you might not hear him today.
I think we will hear him. I think we will.
Probably will.
Oh, wonderful. I'm glad it's going well. And a lot of people there?
There are 81 participants, yes. Some of them are online, but there's quite a good, healthy handful. What I also really like about it is the gender balance, 50-50.
Excellent.
Yeah, 50-50. And that's, I think that's a very important aspect of it.
Yeah. No, we can't claim 50-50, but this week we're running in Dubbo the New South Wales Veterans State Golf Championships.
Oh, yes, you said you were.
And we've got about 120, 130 participants, and about nearly 50 of them are women. So that's pretty good.
Getting there. That is great.
Yeah. I'm having a crack at the championship. I've got. I think the funny story is I said to someone, "Look, I've signed up for the state championships. I don't know why." And he said to me, "Oh no, you got to play." And I said, "Why do you think that?" He said, "Because they need at least 40 players." Gee, thanks for the vote of confidence. So, I've actually played 2 rounds and I've done all right.
Oh, that's
far.
Great!
I'm not going to win. There's a couple of guns that are just not, but I'm hoping to finish top 10.
State championship top 10 will be pretty damn good for golf, which is not an easy game.
No,
but aren't you organising the event? Isn't this a conflict of interest, Andy?
Yeah, I'm part of the committee, but my only major role is to MC the presentation night.
So if you're getting an award.
I won't be giving the awards. I'm just the MC. But I look, that's not even going to be a problem. Not unless I shoot the lights out in the final round tomorrow, but we'll see.
Well, you might do. You might.
You never know.
Putting the lights out is always a good move.
Yes. Golf's like that. Yeah. Could go the other way as well. I've got to keep that in mind. Now, we better get down to why we're here, and that is to talk about things that are happening in astronomy and space science. And one of the things we've talked about on a fairly regular basis is these NASA missions to the moon, known as the Artemis project. Artemis 1 has been and done its thing, a lap of the moon with nobody on board, or maybe a couple of plush toys. But now they're saying that they think Artemis 2 will be on its way at the latest April, but possibly sooner.
Well, it was no sooner than April. That was the deal so far. But the news we've had today is that the launch window, in fact, is being brought forward and could be as early as the 5th of February.
Yes.
So we're looking now at Artemis flying much earlier than we had expected, Artemis 2. And I think one of the reasons for that is that we've been seeing news reports, I'm sure you've caught them as well, Andrew, that the hardware is ready to go, that the Space Launch System, which will take astronauts to the moon, and the Orion capsule, it's all ready to go. And bearing in mind that this mission is essentially a repeat of the November 2022 mission, which was a 25-day mission. It's actually a shorter version of it. But Artemis 1 basically did what Artemis 2 will do. It launched and sent the capsule into orbit around the moon, taking it actually quite a lot further away than the moon's distance, and then bringing it back, re-entering and picking it up in the ocean. So that was a very successful dress rehearsal for what Artemis 2 will be like. And I'm sure the 4 astronauts who are going to fly are trained up to the gunwales, and it will be really great to see them stepping into the spacecraft in February, I think.
Yes, won't that be exciting? And the first time in 54 years, is it? That we've sent people to the moon?
Yes. Well, 1970, no, it's 73.
72 was the last
72,
time.
That's right. So it will be 54. Yes, you're right, 54 years. The point I didn't make is that the astronauts will not land on the moon. That's Artemis 3. Artemis 2 is purely going around the moon and going through all the required maneuvers that will be needed when they actually do go to the moon in Artemis 3. For example, this idea of undocking spacecraft from a module, a service module, turning it around to be facing the way you want it to, and then redocking again. That kind of maneuver, very much the stock in trade of the Apollo era astronauts.
Yes.
But of course, now we've got new technology, quite different technology. A quick shout out to the crew: Christina Koch, Richard Glover. Victor Glover, not Richard Glover. He was on the ABC. Victor Glover, sorry, Victor. Reed Wiseman and Jeremy Hansen. They are the crew of Artemis 2, heavily in training, I'm sure, still, and all ready to take their Orion capsule around the moon to give us a fabulous view. So, yes, the point I think that you were making is that this is the first time in 54 years that astronauts will have gone out of low Earth orbit, which is where they've been in the International Space Station. We haven't had anybody venturing out. And of course, when you do that, when you go between the moon and the Earth, you're in what we might call deep space from a point of view of a spacecraft, which means that you're subject to the sun's radiation and all of that other stuff. So there'll be lots and lots of medical work done on analysing how these astronauts have reacted to that and responded to it.
Yes, and I believe that they will be travelling further than any other human being has ever gone in terms of space travel, because they'll be travelling 9,200 kilometres past the moon.
Yes, that's right. Yeah, yeah.
They still won't be the most isolated humans in history. Michael Collins still retains that because he was by himself.
Yep.
In orbit around the moon, and I believe in his mission, Apollo 11, he was further out than any of the others that were on the command module.
Right. Yes, I think that's correct. I mean, all the Apollo missions had a command module pilot. As you said, Michael Collins was the one for Apollo 11. But I think you're also right that the orbit that Apollo 11 was in was further out from the moon's surface than.
That's how I understand it.
I think you're right.
However, the difference with this one is every other mission we've sent to the moon has had 3 astronauts. This has got 4.
Yes.
So that's a first.
Yep, it is. That's right. That's a big first. New technology. It's a much more spacious capsule, the Orion capsule, which I think will really be it'll be a luxury compared with the Apollo capsules.
I imagine so, and we wish them well. 3 representatives of NASA and 1 Jeremy Hansen from the Canadian Space Agency. That's pretty good too.
Yep.
We'll watch with interest, and as you said, Fred, all the gear is ready to go. This space launch system, the Orion capsule, which had a couple of glitches coming back to Earth on Artemis 1, they've fixed that. I think it overheated.
Yes.
And a few other things that they've sorted out. So they're good to go. So, just waiting for the right weather and the right day to set off. So, yes, there'll be more to talk about as we get into the early months of 2026.
There will.
For the Artemis 2 launch. This is Space Nuts, Andrew Dunkley. Oh, if you want to read about that, of course, it's everywhere, but bbc.com has a good story about it.
3, 2, 1.
Space Nuts.
Now, we'll keep the introduction to this one fairly short. Could we have discovered a wormhole, Fred?
It's the usual answer, maybe.
I knew it.
Yeah, maybe. So what we're talking about is a gravitational wave signal. Excuse me, a slight frog in my throat there. Not a Geordie in my throat, just a frog. It's one that was recorded back in 2019. So we've had access to the gravitational wave sky, if I can put it that way, for 10 years now. And in fact, the first gravitational wave signal was on the 14th of September 2015, Marnie's birthday, as it happens. So the LIGO people, the Laser Interferometric Gravitational Wave Observatory, they have been celebrating their 10th anniversary since operations came in. They have been joined by Virgo, another gravitational wave observatory, and since then CAGRO, which is in Japan. So these 3 facilities are currently routinely looking at gravitational wave science. They're seeing exploding or colliding neutron stars coming in 10 a penny. However, this goes back to when it was just LIGO and Virgo. In 2019, there was a very, very different gravitational wave event detected by the two interferometers. You and I have spoken before about the characteristic sound, because it is in the audio frequency regime. Characteristic sound of two neutron stars colliding, or a neutron star and a black hole, or two black holes. It's that chirp sound. It's whoop, with the frequency increasing as these things spin together and then just vanishes when they collide. It's when they undergo what's called the ring down, where the two black holes actually merge.
Yeah.
But this one was nothing like that, and I'm not going to impersonate what it sounded like, but it was more of a crack.
Was it? No.
It could be something completely different, Andrew. Look, I'm sure there's a joke about Uranus you can make with that, but I'm not even going to go there. So it was more of a crack. It was less than a tenth of a second in duration. These normal signals take a few seconds to build up the frequency, and then they disappear with that chirp. But this one was over in 10 seconds. So there has been work done on trying to explain this. It's got a name. All these things have a name. It starts with GW and ends with the date, spelt backwards. So this was GW190521 for the date, which was the 21st of May, 2019. And the best interpretation, which I guess is the, what you might call the standard picture, is that, yes, it is two black holes.
It's about all you've got on your head, Fred.
I'll have to look for the other one. If there's two black holes snaring each other, not two black hairs snoring each other, which I think is what I was going to say. Two black holes snaring each other. In passing, I'm reading the account that is on Science Alert, written by Michelle Starr, an old friend of Space Nuts, with a name that tells it like it is. So that's the standard interpretation. But there's a new paper that has come from astronomers, physicists actually, which is what you need to be to do gravitational waves, I guess, but astrophysics is probably the real name. A physicist in China, University of Chinese Academy of Sciences. We've seen a new interpretation, which is that what this event depicted was not two black holes colliding in our universe, but in another universe.
Whoa.
And that what we're hearing, or what we're sensing, is the gravitational disturbance of an event in another universe that comes through a collapsing wormhole that was basically formed in the merger and collapsed after the end of it. So
that's a huge claim.
Yes, it is, isn't it? So let me quote from Michelle's article in Science Alert. To be clear, the black hole collision right here in our own universe is still the preferred interpretation of the strange signal. But that preference is not strong enough to rule out the wormhole model entirely. And that's basically a quote from the preprint that these scientists in China have published. So it's quite a remarkable thing. Michelle's article is relatively short, although there's quite a lot of detail in there. But the bottom line is, if that was the correct interpretation of GW190521, and anything else we found that was like it, if that was the confirmed interpretation, that it was a temporary wormhole allowing us to sort of hear the echo of excuse me, I'm going to sneeze, Andrew. Sorry about that.
It's that time of the year over here.
I think that was a wormhole collapsing. Yeah, it wouldn't. If that was the preferred interpretation, it wouldn't just suggest that these things exist. Wormholes have been a feature of science fiction as well as science writing. The fact that they theoretically could exist, but we've got no evidence of them. But what she says is it wouldn't just confirm the existence of these things. It also gives us a new way of investigating their properties, and that might lead to a whole new branch of astronomy, wormhole studies. Wouldn't that be extraordinary?
It would be, but it also opens up another thing that's only theoretical, multiple universe theory. So if we've detected the collision of two black holes in another universe and detected it through the opening up of a temporary wormhole, I mean, that's a double bunger.
That is, except that you would need to rule out the possibility that this wormhole was linking two bits of our own universe. Because
yes.
That's one of the things that has been suggested. But maybe the Chinese paper actually has ruled that out. I'm not sure because I haven't looked at the preprint. But yes, it is really rather remarkable. What the scientists in China have done is basically modelled what you would get if you had a gravitational wave signal from another universe coming through a wormhole. And they've modelled that, and they've compared that with this particular event, and they're reasonably happy that their model actually fits the data. In fact, they say that it's comparable with it. I don't think it's as accurate as the black hole merger waveform, which would be a conventional view that you've got two black holes that have merged together in our universe. That's apparently just a very slightly better fit to the observed signal than their wormhole model, but it's still a possible scenario. So I think this will be very much a pathway for further investigation of wormholes, just generally. So what should we expect if wormholes do exist? What should we expect? It's all very well just talking about their
space worms, I imagine.
Yeah, well, there you go. I think you can get tablets for those kind of space worms.
I think you can, yeah.
Anyway, it's a really interesting piece of work. Obviously, quite controversial, quite attention-grabbing, headline-grabbing.
Yeah.
And I'm going to have a look at the preprint, which I haven't had time to look at yet. In fact, I'm clicking on the link now. And it takes me to a paper called Is GW190521 a gravitational wave echo of a wormhole remnant from another universe? What a great title.
That is a great title, and hopefully it's true. I think that'd be great. It would give us something new to study, and we might even work out how to create our own wormholes and travel long distances at the blink of an eye.
Wouldn't that be great?
Wouldn't it be awesome? Yeah.
Yeah, if we had a little...
Certainly get you out of jury duty.
Not necessarily, because if you're in on the other side of the world, they'd write to you and say, look, you've just got to use your wormhole machine. And
That's a possibility. All this exciting stuff. If you'd like to read about that, you can do that at the Science Alert website, sciencealert.com, and read Michelle's article, or you can go to the source, the preprint server on Archive. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Our final story, Fred, takes us into space to see something very rare indeed. An Einstein cross has been spotted. X marks the spot, and they drew a circle around it.
Well, that's kind of what you have to do.
Yes.
In this case, the observations of the Einstein cross weren't made with visible light telescopes or infrared telescopes, but with our old friend ALMA, the Atacama Large Millimeter Submillimeter Array, which we're more used to seeing connected to images of protoplanetary disks. The high-frequency radio radiation from protoplanetary disks is something that is very much the stock in trade of ALMA. But now they've been observing, I mean, they do observe galaxies as well. What they've observed is an Einstein cross. This is, usually it's 4 images of one object in a shape a little bit like the Southern Cross in our Southern Hemisphere sky, which are all images of the same object. But there's something intervening, there's something between them that creates a gravitational lens that splits the light coming from the distant object. As it passes through the gravitational lens in the foreground, it's split into 4 components forming a cross. The reason why this one is particularly rare is that it has a central image as well. It's a a 5-image Einstein cross, and I think there's only one other one that is actually known with gravitational lensing. And so, the story is that this object, the Einstein cross, is the multiple images of a background galaxy known as HERS 3 or HER S3, probably HER S3. That's a galaxy which is 11.6 billion light years away. So we've got a look back time of 11.6 billion years, well on the way to the beginning of the universe.
Yes.
And it's gone past a group of galaxies, a sort of cluster of galaxies, which are in the foreground, and they're only 7.8 billion light years from us, which is still a staggering distance, but that is the gravity source that is bending the space and forming these multiple images. And so it tells us about both objects. It tells us about the distant galaxy of which this is a multiple image. It tells us about the distribution of matter in the foreground galaxy cluster. And the really interesting thing is that what they've shown, the scientists who've done this work, it's a Parisian group based in Paris, or the leader is based in Paris. What they've shown is that the sort of center of mass of the galaxy cluster is off to one side of where the galaxies are. And that in itself is peculiar, because we interpret that as saying that most of the mass in this cluster is in the form of dark matter, and it's the dark matter clump that is kind of offset from the galaxies that we can see. That's not unique. There are other circumstances like that in the universe, but this is quite unusual that, we've got an Einstein cross created by a cluster of galaxies whose center of mass, if I can put it that way, is off to one side because of the distribution of dark matter around it.
Fascinating. I suppose it also begs the question that we're looking at the same thing in 5 different timelines.
Yes, that's right. And that actually adds something really interesting to this. And certainly in the early days of these kinds of observations, Einstein crosses, and it goes back actually to the 1970s. I remember when the first double quasars were being observed, and they're formed by a similar process. There's something in between the quasar and yourself. A quasar is a kind of delinquent galaxy that's multiplying the image. There's a quote from Tansu Dailan, who's at Washington University in St. Louis, wasn't involved in this research, but a very nice quote that says, "The magnification may allow unusually detailed studies of a starburst galaxy at redshift 3, and that's redshift 3 is what tells you it's that far away, 11.5 billion light years, when the universe was less than a fifth of its current age, including its gas, star formation, and possible outflows." And what you really need is some visible variation in the light of the source galaxy, because the light path to form each of these 5 individual images of that object is different. And so you expect these to be delayed. And in fact, that was the thing about the double quasars. You could see variability in an object, which was mimicked by the second image of it. This is how we knew that there were 2 images of the same thing back in the day. An object would get brighter, the quasar will get brighter and there'd be a delay between one image and the other. If you could do that with 5 images, then you can learn an awful lot. There is another quote from one of the investigators. Usually people use quasars for this purpose of time delay, since they naturally vary very rapidly as a function of time. But her S3 is star forming, raising the prospect of detecting a supernova whose light would arrive at each image at different times, giving the time delay. And from that, you can actually work out what the Hubble constant is. And the Hubble constant is still a topic of discussion. We've talked about the Hubble tension several times.
Yeah.
This will give us another way of measuring that, and that will be very interesting.
Yes, that would indeed be quite exciting. Gee, we've covered some really interesting stories today, Fred.
Haven't we just?
If you'd like to read more about that particular Einstein cross story, you can do it at skyandtelescope.org, or you can read the full paper, which has been published in the Astrophysical Journal. We are just about done, Fred. Before we finish, I might just direct people to the Space Nuts podcast group. This is a Facebook page that was created by our audience and has quite a few thousand people, 2,700 members it's got now.
Wow.
People who discuss science and astronomy together, publish stories that they are interested in, ask questions of each other, try to solve all the mysteries of the universe. It's a great little group. So if you'd like to join, it's Facebook, the Space Nuts podcast group. That's what you've got to put in your Facebook search engines, Space Nuts podcast group. There's also an official Space Nuts Facebook group if you want to join that as well. I think it's got around about the same number of members, probably all the same people. Very likely. Quite a few of them anyway.
Yes, I'm sure that's right. I'll check that out. I'm not a big Facebook user, but once in a while I go online. I have to, first of all, find out once again what my password is, because it seems to keep getting changed. So I'll get into Facebook, or Faceache as I call it. It's what my dad used to call me.
Faceache.
Yeah, Facebook, and have a look at Space Nuts podcast group and see what they're saying.
And I've got to shout out to our administrators who do a great job of keeping it all in ship-shape condition. So thank you, Paul, thank you, Misty, and thank you, Steve, and everybody else who's involved. There's a few people who look after it for us, voluntarily too, I might say. Excellent. Fred, we're done. Thank you very, very much.
It's a pleasure, and good to see you again, Andrew, and we'll talk again very soon, I think.
Very soon, I expect, yes. Professor Fred Watson, astronomer at large, and thanks to Hugh in the studio, who couldn't be with us today. His dog Einstein was naughty. He's very cross with Einstein.
Oh.
Jeez. And from me, Andrew Dunkley, thanks for your company. Catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.